I've had some requests to solve out or finish solving out question 15 that we started in class on Monday. So I'm going to solve this one all the way through. That way you can kind of see the whole process from beginning to end. So we started by looking at asymptotes, and that's about as far as we got. So I'm going to pick up where we left off. First thing I want to do is look at x or a y-intercept. So the y-intercept is when x is equal to 0. So I'll start there. Y-intercept is when x is equal to 0, so if I replace all of the x's with 0, I would get 0 squared minus 6x plus 12, minus 6 times 0 plus 12, all over 0 minus 4. So the numerator becomes 12, the denominator becomes negative 4, so we have a y-intercept at 0, negative 3. Good to know. The x-intercepts, we need to look at when y is equal to 0. So the x-intercepts, we know that y is equal to 0. And when y equals 0 for this fraction, in order to make a fraction equal to 0, the numerator must equal 0. So we're looking where is x squared minus 6x plus 12 equal to 0. If I try to factor this, I end up with it being not factorable. I cannot think of anything that will multiply to be 12 and add to be 6. 6 times 2 is 12, but 6 and 2 don't give me 6. 4 and 3, 12 and 1. So this is not factorable. Since this is not factorable, I'm then going to try using the quadratic formula, because the quadratic formula can give me a decimal value for the x-intercepts. Quadratic formula is negative b, so that would be positive 6, plus or minus the square root of b squared, so that's negative 6 squared, minus 4 times a times c. And then it's all over 2 times a. If I look at the discriminant, the part under the radical, negative 6 squared is 36, 4 times 12 is 48, 36 minus 48 gives me a negative number under this radical, which means that there are no x-intercepts for this function. Okay, so we've looked at that part, no x-intercepts. Okay, the next thing then, before we even get into any calculus, we're going to look at asymptotes. So we just noticed, based off of trying to find the x-intercepts, that the numerator does not factor. What that means then is x minus 4 in the denominator is a non-removable discontinuity. Since x minus 4 is non-removable, that means there is a vertical asymptote on this graph. Remember, removable would be a hole. There is a vertical asymptote on this graph at x equals 4. Okay, the last thing we need to look at then is the horizontal or oblique asymptotes. So let's see if we can find that. So we already did this one. We found the limit to be infinity. I'm just going to do the division once again. So I'm going to divide x minus 4 into, what was the, x squared. So I put x squared here, that's x. This is negative 4x. I need this to be negative 2x so that these two will add up to be negative 6x. That's the term in the middle. So that means I need to multiply this by negative 2 because negative 2 times x. And then negative 2 times negative 4 is 8. Ugh, I keep hitting my button. Okay, let's try it this way. Okay, and I need this to be 12. I need the constant to be 12. So what that means is I need to add 4 to this. And 4 then will be the remainder because I cannot multiply x times anything to become 4, at least nothing rational. So what we found is that there is an oblique asymptote at y equals x minus 2. Okay, so we found asymptotes, we found intercepts. Now it's time to do some calculus. We're going to find where is the function increasing, where is the function decreasing, so that we can get a little better picture here. we'll also be looking at where the function is concave up or concave down. So let's see what we can do here. I'm going to rewrite the function so we can find the derivative. I'm going to use a different color. So the function was y equals x squared minus 6x plus 12. Sorry for all the back and forth, I just can't remember. Minus 6x plus 12 over x minus 4. Okay, we'll differentiate. In order to find the derivative, we need to use the quotient rule. So y prime, finding the derivative of the numerator, is 2x minus 6, and the denominator is x minus 4, minus the numerator without changing anything, multiplied by the derivative of the denominator, which is 1. All of this is over the denominator squared. Now, in order to solve this, to find the critical numbers, we need to find where is this equal to 0 and where is this undefined. So it is going to be in our best interest to do some simplifying in the numerator. Okay, so in the numerator, if I multiply, so if I FOIL these first two, I get 2x squared minus 8 and minus 6x would be minus 14x. Negative 6 times negative 4 is 24. If I distribute the negative to the second set of parentheses, I end up with negative x squared plus 6x minus 12. And that's multiplied by 1, not changing anything. Okay, now if I combine those two things together, 2x squared minus x squared, it's just x squared. Negative 14x plus 6x is negative 8x. And positive 24 minus 12 is positive 12. All of this is over x minus 4 squared. So remember, yesterday we looked at a couple different things. We said that in order to determine critical numbers, there are a couple places where that can happen. That can happen where the derivative is equal to 0 and where the derivative is undefined. So the critical numbers then where the derivative is equal to 0 is when the numerator of this fraction is equal to 0. So the first thing I'm looking for is where is x squared minus 8x plus 12 equals 0. This will make the derivative equal 0. The other thing I'm looking for is where does x minus 4 squared equal 0? Because where the denominator equals 0 is when the derivative is undefined. Okay, so in the numerator, if I factor this, this factors to be x minus 6, x minus 2. In the denominator here, the x minus 4 squared, it's already factored. So I can see from this then that I have 3 critical numbers, 3 places where we have a potential min and potential max. Now, this isn't really realistic because we've already said up above that x equals 4 is a vertical asymptote. If 4 is a vertical asymptote, there is no way it could be a minimum or a maximum. But I'm still going to include it in my table. I know that this is not a critical number. I know that 4 is not a min or a max. But I'm still going to include it in my table because a vertical asymptote is a pretty key point on a function, and it's important to notice what's happening to the function around that vertical asymptote. So even though there is absolutely no way that could be a min or a max, I'm still going to use it in my table, in my little number line. Okay, I'm going to find the second derivative though before I use the number line. I'm going to use another different color so it's easier to see. I will use this green color here. So I'm going to find the second derivative just to get all of this done at one time. Second derivative, we get to use the quotient rule again. So the derivative of the numerator is 2x minus 8 multiplied by the denominator without changing anything minus the numerator unchanged multiplied by the derivative of the denominator. You know, when we find the derivative of the denominator, you're going to need to use the chain rule because we have an inner function and an outer function. So using the chain rule, I'm going to multiply the 2 out in front without changing x minus 4, and now that's to the first, multiplied by the derivative of what's inside, so that's 1. And then over the denominator squared is going to be x minus 4 to the fourth. Now we need to set this equal to 0 as well, because remember that points of inflection can occur when the second derivative is 0 or when the second derivative is undefined. But I don't really want to multiply the numerator all the way out. What I do notice, though, is that all of these terms have an x minus 4 in common. So if I factor an x minus 4 out of the numerator, what that leaves me with in this term then is still a 2x minus 8, and I have 1x minus 4 left over. I'm going to move this down because of what's going to happen next. I need some space. Okay, so I've got 1x minus 4 left over from that term. If I take an x minus 4 out of the second term here, I'm left with a 2 and an x squared minus 8x plus 12. Okay, and then the denominator, I've got x minus 4 to the fourth. Oops, I was getting ahead of myself. So what I'm noticing here now is that I can cancel an x minus 4 from the numerator and 1 from the denominator. And instead of rewriting it, I'm going to leave it like that for now, for the sake of time. Okay, so I've simplified this a little bit. I'm going to now do some multiplication in the numerator to make this a little bit easier to solve. So I'm going to FOIL these first two. That's 2x squared minus 8 minus 8, so that's minus 16x plus 32. I'm going to distribute negative 2 to this entire set of parentheses, so it's negative 2x squared plus 16x minus 24. If I simplified the numerator now, 2x squared and negative 2x squared cancel, negative 16x and positive 16x cancel, so all I'm left with is 32 minus 24. So this second derivative is 8 over x minus 4 to the third. All right, so looking for potential points of inflection, I need to find where is the second derivative equal to 0, where is the second derivative undefined. So in order to make the second derivative equal to 0, I need to set the numerator equal to 0. And in order to figure out where the second derivative is undefined, I need to set the denominator equal to 0. So in the numerator, obviously, 8 does not equal 0, never will. There are no places where the second derivative is equal to 0, so no points of inflection could come from that. The next thing I see in the denominator, when x is 4, that will make the denominator 0. So x equals 4 comes up again. We know that it is a vertical asymptote. That could be a place where the graph changes concavity. So we're going to keep all of this in mind. All right, it's time for the x-axis thing, the little chart. So I'm going to make my chart. Oops. What color do you think? Let's do pink. So I'm going to make this chart. Ooh. Notability to the rescue. This is negative infinity to positive infinity. We have some key points here. We know that 2, 4, and 6 were important points for us. Those were the critical numbers, and 4 was also a place where there could be a change in concavity. Okay, so I'm going to use this to inform me about f of x, and I'm going to find the value of the first and second derivative all at the same time, just to save me a little bit of time here. All right, so between negative infinity and 2, I think that 0 is a pretty important point. So I'm going to plug 0 into the first derivative. I'm going to bring the first derivative down so that I can see it a little bit easier. I'll move all this up a little bit. Okay, so if I plug 0 into the first derivative, I have 0 minus 0 plus 12. So that gives me 12 in the numerator. And then 0 minus 4 squared is positive. So I have a positive 12 in the numerator. I have a positive in the denominator. So that means that the first derivative is greater than 0, which means that the function is increasing. I'm going to plug 0 into the second derivative as well. If I plug 0 into the denominator, 0 minus 4 is a negative number, and that negative number cubed is still negative. So positive 8 divided by a negative number is negative, which means that the function is concave down. Okay, now I'm going to pick a number between 2 and 4. The easiest one, of course, would be 3. I'm going to plug 3 into the first and the second derivative. So if I plug 3 into the first derivative, 3 squared is 9. 9 minus 24 is negative 15. Negative 15 plus 12 is a negative number. If I plug 3 into the denominator, because that's squared, that will always be positive. So negative divided by positive, that means that the first derivative is negative, which means the function is decreasing on that interval. If I plug 3 into the second derivative, 3 minus 4 is a negative number cubed is negative, so still concave down. That's a down arrow if you weren't sure. Okay, now 5, plugging in 5. 5 squared, 25. 25 minus 40 is negative 15 plus 12, so the derivative is still negative. Because 5 minus 4 is positive. Let me make sure, because 25 minus 40, negative 15. Yeah, that's negative. Okay, the second derivative, plugging in 5. 5 minus 4 is a positive number, so that means the second derivative is positive. So that means this function is decreasing. And definitely the concavity has changed. So now the function is concave up. Okay, last but not least, let's plug in 7. So if I do 7 squared, that's 49. 49 minus 7 times 8, so 49 minus 56 is negative 7. Negative 7 plus 12 is positive. Divided by a positive is positive. And then the second derivative, if I plug 7 in, the denominator is positive. So we know that this is still concave up. So now the function is increasing, concave up. All right, let's graph. We know a bunch of things. Let's do some, let's write the answer first and then we'll graph it. So from up above, we knew that we had an x-intercept at, been so long now I can't remember, at 0, negative 3. I mean a y-intercept at 0, negative 3, no x-intercepts. So x-intercepts, none. Y-intercept, 0, negative 3. We have a vertical asymptote at x equals 3. We have an oblique asymptote at y equals x minus 2. We know that f of x is increasing from negative infinity to 2 and from 6 to infinity. F of x is decreasing from 2 to 4 and from 4 to 6. Notice I didn't just say from 2 to 6. That's because there is a vertical asymptote in the middle of that domain. So we need to make sure we're keeping them in 2 different groups, 2 different intervals. Okay, we know that f of x is concave up from 4 to infinity. There was no vertical asymptote in the middle of that interval, so I can just say the whole section. And then f of x is concave down from negative infinity to 4. Okay, that's the solution. If I ask you to analyze this graph, this is the analysis I'm looking for. And now I want you to graph this. Okay, so we're going to graph this with all of the points that we know. We're going to get as close to being accurate as possible. So I'm going to, never mind my non-straight lines, I'm going to graph the things I know. No x-intercepts. Y-intercept at 0, negative 3. I have a vertical asymptote, not at x equals 3, but at x equals 4. You probably were thinking that all along, weren't you? So we have a vertical asymptote at x equals 4, 2, 3, 4. We have an oblique asymptote at y equals x minus 2. So 2 and then up 1 over 1. So we've got an oblique asymptote at y equals x minus 2. I can tell because the function changes from increasing to decreasing at x equals 2, so the first derivative changes from positive to negative. I know that at x equals 2, we're going to have a relative maximum. And so I'll have to plug 2 in to figure out where that is. And I can see that the function is changing from decreasing to increasing at x equals 6. So that means that the first derivative is changing from negative to positive. We know that there is a relative min at 6 comma something. The concavity changes at x equals 4, but it's not a point on the graph. It's a place along the x-axis where the concavity changes. So I'm just going to say concavity changes at x equals 4. By saying it's a point of inflection, that doesn't make sense because there is no point on this graph where the concavity will change. It's just a moment in time the vertical asymptote makes that change happen. So let's find the ordered pair for the relative max. If I plug 2 into the original function, and for some reason I cannot remember this function, so if I plug 2 into the original function, that's 2 squared, minus 6 times 2 plus 12 over 2 minus 4. 2 squared, that's 4. And then negative 6 times 2 is 12. Negative 12 plus 12 is 0, so we get 4 on the top. 2 minus 4 is negative 2. So we have a y value of negative 2 then for the relative max. Okay, I'm going to plug in 6. I have 6 squared minus 6 times 6 plus 12 over 6 minus 4. So 6 squared is 36. 6 times 6 is 36. 36 minus 36 leaves me with 12 on the top, 2 on the bottom. 12 divided by 2 is 6. And some of you are thinking, hopefully thinking now, wait a minute. How can there be a relative maximum at 2, negative 2, but a minimum at 6, 6? 6, 6 is above 2, negative 2. I'll show you. Trust the math. So we're going to graph those 2 points. At 2, negative 2, we have a relative max, and at 6, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, we have a relative min. All right, let's put all of this together now. The function from negative infinity to 2 is increasing and concave down at the same time. So increasing and concave down all the way up to this point. Whoops. And then at 2, the function changes so that it's decreasing up until 4. But we also know that the function is still concave down, which makes sense because this was the relative maximum we were looking for. Okay, now from 4 to 6, the function is decreasing, and from 4 to 6, the function is concave up and decreasing, and then the function changes from increasing from 6 to infinity, but still concave up. There we go. There's your graph. Pretty cool.